Hello and welcome to the North Carolina Smart Grid Basics webinar series. We're very pleased you decided to take a little time out of your schedule to join us today. My name is Alex Glenn, and I work with Advanced Energy as a training consultant and instructional designer. I've worked in the energy industry for 15 years, and I'm happy to be your host and facilitator for today's webinar. As an independent nonprofit that works with most of North Carolina's electric utilities, Advanced Energy's mission is to help our state's electric utility customers get the most value out of the money that they spend for energy. To help our state's residents make well-informed energy decisions, we want to share information about new technologies and services when we believe they can offer value, and we also want to share any concerns that may present risk. This webinar series is being developed using North Carolina Public Benefits Funds administered by Advanced Energy and Duke Energy, along with generous technical support from North Carolina's electric membership cooperatives, Duke Energy, and Dominion Power. North Carolina's electric utilities are in the midst of modernizing their power generation and distribution systems. This transformation of our electric grid offers improved performance and growth opportunities for citizens, communities, and businesses. We are pleased to bring you information about smart grid technologies and systems that are being deployed in North Carolina and how you might be able to benefit from them. Today, we bring you the second webinar in our series, Solar Power and Grid Integration. And as a reminder, we have additional smart grid topics planned for the remainder of 2017, including smart meters and AMI, microgrids and grid resiliency, and self-optimizing systems. Please feel free to join us for the rest of the webinars in the series, as each one will cover new information as well as relevant connections between the different technologies. Today, we'd like to hear from you during this webinar. Please feel free to post your questions or comments in the Q&A box on the right side of the screen. We will answer as many questions as we can at the end of today's presentation. I'd also like to mention the website that we have developed where we will be making additional smart grid resources available to you. We'll be posting case studies, educational videos, upcoming events, and links to all of these resources. So please be sure to visit ncsmartgrid.org to access more information. As a note, a recorded version of this webinar will be made available to you. We will send a follow-up email to access that webinar recording, as well as the additional links to smart grid resources. In today's webinar, we will recap a couple of key points from our Smart Grid Basics webinar and dig deeper into the topic of solar energy in North Carolina. We will provide an overview of solar power and solar technology, explore North Carolina policies and economic factors, and discuss benefits and challenges for integration into the grid. We could spend a lot of time exploring and discussing any one of these topics. Our goal today is to stay at a relatively high level so that we can cover a wide range of topics that are playing a role in the success and growth of the solar industry in North Carolina. I'd like to take time to introduce you to our presenter, Cyrus Doster. Cyrus is an energy consultant here at Advanced Energy, and he's worked on our building science and engineering teams. His current work focuses on electric vehicles, solar assessments, and smart grid education. At this point, I'm going to turn it over to Cyrus, who will give us a little more detail about today's agenda and will also deliver today's presentation.
Thank you, Alex, and thanks to all of you for joining us today. As Alex mentioned, today's session focuses on solar power and this slide gives a bit more detail on what we'll be covering. So first I want to clarify that we'll only be talking about photovoltaic, or what's referred to as PV technology today. We won't be talking about solar thermal systems. Solar thermal systems collect the heat from sunlight, whereas photovoltaics convert the energy in sunlight directly to electricity, and that's the technology we'll be discussing today. After we review some key points on smart grid and the state of solar power in North Carolina, we'll talk about the basic elements of a solar generator. Then we'll address key economic factors and a pair of legislative and regulatory policies that have a significant impact on solar industry growth in our state. After that, we'll turn to several examples of benefits that solar power offers. And finally, we'll round out the conversation by discussing some of the technical challenges to integrating solar power onto the electric grid and why they're important to address. I also want to let you know that similar to our first webinar, we're using a hybrid model for today's session, and the upcoming section is pre-recorded. There's a good bit of content to cover, and this section will run approximately 33 minutes. While you're watching, please do feel free to submit questions, and we'll do our best to address them when we return to live discussion. Let's begin. We're going to start today with a quick review of definitions that we shared in the Smart Grid Basics webinar, as well as an overview of solar generation in North Carolina. To review a few of the definitions we presented in the Smart Grid Basics webinar, let's cover the ones we have here. The electric power grid is the system of wires, switches, and other equipment that brings electricity from where it is generated to where it is needed. A smart grid integrates new sensors, controls, and communication networks with a traditional power grid. And solar power increases the need to modernize our grid because it is a variable and distributed resource. We'll talk about variability later in the presentation. As far as solar being a distributed resource, that means that solar is generally smaller than conventional generators, and it is generally located closer to the loads that use it. This next slide will give an idea of what we mean by distributed energy resources. The traditional grid has large central generators sending power in one direction to customers, often many miles away. A typical conventional generator can produce more than 1,000 megawatts of power. In fact, the average power output of the top 10 generators in North Carolina is more than 1,700 megawatts each. In contrast, solar facilities are much smaller and are located closer to the customers who are using the power. A typical solar generator connected to the transmission section of the grid might be 50 megawatts. A typical solar generator connected to the distribution section of the grid could be 5 megawatts, while the average solar system installed on a home is down around 5,000 watts, or just 5 kilowatts. So as a distributed resource, solar is smaller, but it can be installed in greater numbers, and you can see that with solar installed, the grid needs to handle power flow in more than one direction. Speaking of large numbers of solar installations, as of the end of 2016, North Carolina had installed over 3,000 megawatts of solar capacity, according to the Solar Energy Industries Association. That amount is second only to California, and the SEIA estimates that this is enough power for approximately 340,000 homes. Now, to keep that solar capacity in perspective, that 3,000 megawatts, which can also be expressed as 3 gigawatts, is only about 3% of our state's total electric capacity. This data from the Energy Information Administration shows that coal, nuclear, and natural gas still dominate our electricity production. If we zoom in to the top portion of the graph, solar is represented by that yellow wedge, and you can see that it is still smaller than biomass and hydropower, but solar is growing while they remain constant. Now let's talk about the basic technologies that generate this solar power. One of the advantages of solar is that it is very scalable, meaning that it can be cost-effective to build facilities in that wide range of power outputs that you saw in the comparison of distributed resources to central generators. Regardless of the overall size, solar generators that are connected to the power grid have the same basic components: solar panels, inverters, transformers, and interconnection switches, and the variation will be in the number or size of the different parts. At this time, solar development in the state is dominated by large-scale projects, so most of what we cover today will be from that perspective, but we'll also weave in some important points about smaller-scale generators. So naturally, we should start with the solar panel. This image shows a small array of panels that are mounted together. The yellow outline indicates one single panel, and these panels are the part of a solar facility that converts the energy in sunlight into electric power. A common solar panel like these can produce from 200 to 400 watts each, so even at the high end of that range, it would take 4 or 5 panels to produce the power that's needed by just one medium-sized microwave or hairdryer. It's also important to know that before solar panels can provide power to the devices and appliances in our homes, we need to do a conversion. That is because solar panels produce DC power. That stands for direct current, and it is the same form of electric power created by batteries. It is not the same as the AC, or alternating current, that travels across the electric grid and comes out of the outlets in your home. We generally do that conversion from solar panel DC to grid-compatible AC using two pieces of equipment: inverters and transformers. An inverter is the device that converts the DC power from the solar panels to AC power. The transformer takes that AC voltage from the inverter and boosts it to a much higher voltage that matches the voltage on the section of the grid it is connected to. To give you a frame of reference for a common project, the battery in your car runs at 12 volts DC. At a typical grid-scale solar facility, the panels are wired together to create about 1,000 volts DC. That solar voltage is then converted to 600 volts AC by the inverter, and commonly boosted by the transformer to around 24,000 volts AC for the grid. So needless to say, these are hazardous levels of electric power that require attention to all safety warnings and instructions. While it is common to have large inverters, like this one, that serve many panels at one time, you might also hear about projects that use microinverters, and as the name implies, they're much smaller. They are actually small enough that each panel can have its own microinverter, and then the AC power from all the microinverters is combined to go into the transformer. Finally, we need to connect the AC power from the transformer to the electric grid. That generally requires a series of switches, meters, and safety devices to allow the facility to be connected and disconnected, monitored, and protected from power faults, very similar, if not the same, as the equipment used on the grid itself. So that's a basic overview of grid-scale solar technology and how it connects to the grid. Now, let's look at some of the economic factors that have fostered the growth of the industry that is putting that technology into operation. There are two economic factors that relate directly to solar facility construction that I'd like to mention now: solar panel costs and workforce. Later, we'll cover some state and local policies that also have important impacts on the economics of solar generation. One of the most important factors affecting solar installation growth has been the significant price declines for complete installed systems. On a per watt basis and adjusted for inflation, prices for solar have dropped from 60 to 70% since 2010. Another factor that has supported the growth of solar in our state is the high quality of North Carolina's community colleges and universities. They offer multiple programs that create a skilled workforce for our solar industry. in jobs focused on construction, design, operations, maintenance, or engineering. This includes internationally recognized research programs that are developing and testing next-generation solar and grid technologies. And I also want to note that North Carolina is fortunate to have a large population of former military service members as a well-trained resource for our solar industry. Now, let's turn to some of the regulatory policies that have made North Carolina particularly attractive for solar development. Two key pieces of legislation have provided powerful incentives for the growth of North Carolina's solar industry. The first is the Public Utility Regulatory Policy Act of 1978, which is typically referred to as PURPA. Second is the Renewable Energy and Energy Efficiency Portfolio Standard, which was passed in 2007 as part of State Senate Bill 3. These policies are two of the reasons we need a smarter grid, since they have helped drive the growth of solar power. Starting with PURPA, there's interesting history behind its implementation in North Carolina. In the 1970s, North Carolina was experiencing approximately 10% annual growth in our demand for electricity. This rapid growth was driven by a growing population and the dramatically increasing use of air conditioning. There were also national concerns about the energy situation at that time, due to a natural gas shortage and dependence on foreign fuels. So, the U.S. Congress passed PURPA in 1978, and it required utilities to purchase power from a privately owned generator if that generator was 100 kilowatts or less in size. The utility had to pay the generator an amount over a fixed term that was equivalent to the avoided cost that would have been incurred if the utility had had to build its own generator. In other words, there was a goal that customers would not be adversely affected under that policy. However, North Carolina had no takers with the 100 kilowatt cap, and PURPA allowed states to establish broader standards, so we raised our cap to 5 megawatts in 1984. At the time, solar was not technically mature, and it was very expensive, so the 5 megawatt rule was not anticipated to drive solar generation. Rather, it was thought that new hydropower generators might be built. Despite that, even with the higher cap, we did not get appreciable independent power production until another policy helped to create demand. That next policy was the North Carolina Renewable Energy and Energy Efficiency Portfolio Standard, referred to as the NC-REPS, which was passed in 2007 as part of Senate Bill 3. The portfolio standard established a timeline for utilities to meet specific renewable energy generation targets. The ultimate goal for investor-owned utilities, like Duke Energy and Dominion NC Power, is to satisfy 12.5% of their electricity demand with renewables or energy efficiency by 2021. Electric cooperatives and municipal utilities must meet a 10% goal by 2021. The portfolio standard boosted the growth of our solar industry by setting a specific goal for solar generation. In conjunction with improved technology, falling prices for solar systems, and the PURPA policy, it drove rapid growth in grid-scale solar projects. Now the cost of solar has dropped significantly, and there are some concerns about integrating larger amounts of solar onto the grid. North Carolina utilities have asked the Utilities Commission to lower the PURPA cap from 5 megawatts to 1 megawatt, and to switch to a competitive bidding process for solar systems that are larger than 1 megawatt. If those changes are implemented, we would likely see the pace of solar development slow somewhat in the coming years. However, if solar continues to decrease in costs, that could actually outweigh any slowdown from the change in the PURPA rule. And keep in mind that there are already about 2,000 megawatts of new solar projects planned that would likely be grandfathered on the existing PURPA contract terms. That would build on the 3,000 megawatts that we already have installed. So that wraps up our basic overview of solar-related policies, technology, and economic factors. Now let's move on to talk about how solar benefits North Carolina. The transition to a smart grid offers a wide range of potential benefits, which generally fall into at least one of these categories: customer service, municipal readiness, community sustainability, and economic growth. Next, we'll cover some examples of how solar power is delivering benefits in each of these areas. In the area of customer service, solar generation can help to meet customer demand for cleaner energy sources. Whether customers choose to purchase solar energy through their utility, or they invest in their own system at their home or place of business, the availability of quality installers and the affordability of solar power enables customers in North Carolina to make that choice. Options like Brunswick Electric Membership Cooperative's Community Solar Program or NC Green Power are examples that allow the purchase of solar power by customers who can't or don't want to own their own systems. For customers who do own their system and want it to be connected to the grid, there are several different options that will depend on their utility and the size of their solar facility. Microgrids are independent power systems that can take over for the electric grid during a power outage, and they can help local governments keep critical systems online. These pictures show the McAlpine microgrid, which is owned and operated by Duke Energy in Charlotte, and it provides seamless backup power for a fire station that is located right next door. This microgrid incorporates solar panels to increase the length of time that it can provide power without needing any conventional fuel supply. In addition to fire stations, solar can also support backup systems that serve critical communications, traffic control, water treatment, and wastewater treatment facilities. Beyond municipalities, military installations are another area where solar can enhance reliability and resiliency in North Carolina. More and more businesses, institutions, and local governments establish emissions reduction targets. Solar generation provides an effective tool to reach those goals. The state's current solar generation reduces carbon dioxide emissions by over 750,000 tons per year, and it's projected to reduce those emissions by 3 million tons per year by 2022. In addition, once a solar facility is in operation, these generators result in dramatically reduced emissions of nitrogen oxides, sulfur oxides, and particulate matter, and they pose very little risk of water contamination. Besides environmental sustainability, individuals and organizations may simply want to use solar generation to provide emergency power or to reduce their conventional energy expenses. While the first cost of a solar system may be more expensive than a conventional generator, its life cycle cost may actually be lower due to sunlight being a free fuel source. In addition, solar systems have few moving parts that need maintenance or repair, reducing those types of expenses. Earlier, we talked about some of the economic factors that are supporting the growth of solar. That solar development can then lead to significant economic growth in the surrounding community and state. As an example, Catawba County is one of the top counties in the state for the amount of grid-scale solar that's been installed, and the city of Conover has been on the leading edge of that development. One very important factor in the demand for development there is Conover's proximity to electric grid infrastructure. That has made interconnection more feasible and cost-effective. Another factor is that different municipal requirements for land use can have a significant impact on solar development. Where jurisdictions require rezoning or conditional use permits, development has slowed. But in jurisdictions like Conover, which permit solar development as an accessory use by right, development has been strong. One of the most important economic results is that converting land for use by solar generators can raise income for the property owner. It can also raise tax revenues for the local jurisdiction, with the increase ranging from a factor of 2 to a factor of 10 in Conover. As another example, the O2 Energies project in the lower photo adds approximately $2 million to the tax base of Rowan County. And as you can see, solar development doesn't necessarily rule out agricultural use of the land. However, livestock grazing does require additional planning and may be restricted by ordinances that apply within typical municipal boundaries. I'd like to acknowledge that there has been concern expressed over the amount of cropland being converted to solar generation, but a recent study by the North Carolina Sustainable Energy Association and the North Carolina Department of Agriculture has documented that as of the end of 2016, a total of only 0.2% of North Carolina cropland has been converted to solar use. That's about 9,000 acres, which is less than 1% of the 1 million acres of cropland that have been converted to commercial and residential use over the past decade. For a wealth of additional detail, visit the Sustainable Energy Association's website and download their North Carolina Solar and Agriculture Report. Last, but certainly not least, solar development has created significant employment. In its most recent Clean Energy Industry Census, the Sustainable Energy Association reports that over 330 companies in the North Carolina solar industry employed more than 5,400 full-time equivalent positions in 2016 and brought in over $1.4 billion in revenue that year. Now, of course, no technology is perfect, so as we aim to realize all these benefits from solar generation, there are several challenges to be faced. Because this webinar series is covering technologies as they relate to the development of a smart grid in North Carolina, our focus today will be to look at a few of the challenges that relate to integrating solar power with the grid. These are by no means the only challenges for solar. Issues like financing, business models, equipment availability, and permitting all warrant additional conversation. But today we're just going to look at a few of the technical challenges of integrating solar power on the grid. These include the variability of solar power, how that power aligns with peak loads, a phenomenon called the duck curve, and quality assurance. The reason that the variability of solar power is important is that in proper operation, the power grid must constantly match the supply of electricity to the load as the load varies. Solar variability is predictable in the sense that we can very accurately know the number of daylight hours for any given day. But we are still working on computing tools that can predict and track cloud cover and determine its impact on how much sunlight will be available. The graph on the left shows the output of a solar facility on a good production day. April 10th is almost perfect. The plot on the right shows a day with particularly high variability as a comparison. The power output doesn't drop to zero, but it repeatedly cycles as much as 70% up and down for more than half of its productive hours that day. So this illustrates how solar can create additional need for power management, especially on the circuit that it is connected to. Another challenge to integrating solar power onto the grid is whether or not the solar generation matches up with the times when there is the most demand for electricity, called peak load. The blue curve at the top of this graph represents the rise and fall of electric power load over a typical winter day. The vertical axis indicates the amount of power, and the horizontal axis shows the time of day, from midnight to dawn, through lunch, into the evening, and then midnight of the next day. You can see that the winter peak load typically occurs before dawn, when heating demand is at its highest. Then there is a secondary peak in the evening as people return home from work or school. I was surprised to learn that in recent years, this pre-dawn winter peak has been as high or higher than our summer afternoon peak, which we'll talk about on the next slide. As a matter of fact, our all-time generation record was set on February 20th, 2015, during the extreme cold weather that we had that winter. Now, let's add in a curve to illustrate solar generation. That orange line at the bottom shows a typical solar generation profile, and I want to note that it is not to scale. Our solar generating capacity is not this high yet compared to the total grid load, and I've shown it larger simply to make it easier to compare the profiles. The most important detail is how the curves compare over time. Since the solar generators peak in the early afternoon, the solar peak does not line up with either of the winter daily load peaks, and those loads must be met by non-solar generators. In this next slide, we're looking at a summer scenario. The blue curve at the top of this graph models the rise and fall of electric power load over a typical summer day, and it shows that there is just one peak that occurs in the late afternoon and early evening when air conditioning demand is at its highest and people are arriving back at home from work or school. The orange line at the bottom again shows the solar generation profile, and you can see that in the summer, solar power aligns better with the electric load. It rises with the load in mid-morning, peaks in the early afternoon, and then declines as the sun sets, even though the electric load is still increasing. Now, let's add a third curve to this graph to help see the impact of the solar supply on non-solar generators. The green curve in the middle represents the power that must be provided by non-solar generation. It represents the electric load in the blue curve minus the solar supply in the orange curve. So you can see that as solar power ramps up in the middle of the day, other generators ramp down. And then as the sun sets, the non-solar generators ramp back up to match the load into the night. Now let's focus on that green curve and see how non-solar generators are affected as we put more and more solar onto the grid. So taking that summer load graph and thinking about how it will change as more solar generators are added to the grid brings us to this graph, which is often called the duck curve for the silhouette that it creates. This is a complicated topic, so let's take a minute to lay out what is going on. The darkest green curve represents the non-solar generation that is needed to meet the total electric load as shown in the previous graph. And as we saw, that dip a little after lunchtime is due to solar generation getting to its highest level for the day. Over the coming years, we will have more and more solar added to the grid, and the lighter green curves are showing that as that happens, the after-lunch dip in the non-solar generation will get deeper. The challenge comes in the afternoon. As the sun starts to set, the non-solar generators have to ramp back up to compensate for the declining solar power. And those non-solar generators have to match up with an increasing load. People are going home from school or work and turning on lights, appliances, and electronics. Air conditioning takes a lot of power, and it is also peaking, with the temperature hitting its high mark for the day. That time of increasing load in the afternoon and evening is called the ramp period, and the duck curve shows us that as we add more solar generators to the grid, the increase in power needed from non-solar generators during that ramp period gets steeper. That rate of increase is called the ramp rate, and grid operators need to manage non-solar generators carefully during that time, because not all of them can increase their power as quickly as it is needed. A common idea for slowing the ramp rate is to limit the amount of solar on the grid. But another option is to reduce the peak load instead. Using market incentives like time of day billing or credits for reducing demand would help to control the ramp rate, as would incentives for thermal or battery storage. We could even orient some solar generators to the west so that they produce more power later in the day. So we have several options for dealing with this challenge while we gain the benefits of more solar power. If you want to learn more about ramp rate and the duck curve, a great place to start is the recent report from the Scott Madden Consulting Group titled Revisiting the Duck Curve. They analyzed detailed data from the California grid operator and discovered some surprising trends that will likely also apply here in North Carolina. The last challenge I'd like to discuss today is the need to ensure that the design, installation, and operation of the solar generators is of sufficient quality to match the safety and reliability of the grid they are connected to. Many industries go through growing pains, and with its rapid growth, the solar industry is no exception. Solar generators are now built at sizes large enough that if they experience a failure, it can disrupt other customers that are connected to the same circuit or substation. For example, certain industrial and commercial facilities are susceptible to power quality issues. If a solar generator causes a voltage sag, it could cause those facilities to disconnect from the grid and shut down, idling dozens or hundreds of workers and causing the loss of work in process. Some problems that Advanced Energy has encountered during solar generator assessments include inverters having incorrect settings, insufficient grounding or grid interconnections, and improper fault detection. As a result, we're working with North Carolina utilities and solar developers in a collaboration to make sure that construction standards are clear and well understood. Proper installation is crucial to personnel safety, equipment protection, and reliable grid operation, and everyone is committed to those goals. To sum up this section, we definitely have challenges to the successful integration of solar power with the grid at higher and higher levels. Those challenges can be technical, environmental, or operational, but they all seem to be manageable with good planning, engineering, and implementation. In fact, challenges like variability and peak load alignment create additional opportunities. As one example, North Carolina has companies working to deliver battery storage systems that solve those issues and create additional job growth and value in the state. Battery storage could very well be the next clean energy success story that North Carolina can help to lead, as we are doing with solar.
That brings us to the end of the solar power and grid integration presentation, and I hope it's given you a helpful overview of the technology and the important issues to keep in mind as you consider the opportunities that it can offer you, your business, or your community. At this point, I'm going to turn it back to Alex to recap and take us into the Q&A session.
Thanks so much, Cyrus. You certainly covered a lot of ground and definitely helped all of us gain a better understanding of solar power, as well as all the challenges and the opportunities of integrating solar into our electric grid. I think it will be very interesting to see how businesses and industries in North Carolina adjust to the integration of solar as part of our transition to a smart grid. Before we get into the Q&A period, we'd like to remind everyone that the conversation will continue in 2017 with additional webinars on smart meters, microgrids, and self-optimizing systems. We're excited to take a deeper look at these technologies, and we hope that you will join us again. Please keep a lookout for an email invitation with registration information. And as a reminder, we'll be sharing case studies, educational videos, upcoming events, and links to deeper smart grid resources at ncsmartgrid.org. At this website, you'll also find links to the resources Cyrus referenced in this webinar, such as a report from the NC Sustainable Energy Association titled North Carolina Solar and Agriculture, as well as a report from Scott Madden Management Consultants titled Revisiting the California Duck Curve. Just a quick note that we will send an email with resource links, a copy of today's webinar recording, and a brief satisfaction survey. Please help us by filling out the survey so that we can continue to make these webinars valuable for you, and as always, your feedback is greatly appreciated. At this point, we'd like to take a few minutes to answer some of the questions and comments that have come in during the webinar. Please understand that we may not have time today to answer all of the questions, or we may not have an immediate answer to a question. In either case, we will do our best to follow up with you after doing some research or finding the best resource for you. Cyrus, let's take a look at some of the questions that have come in.
Thanks, Alex. I'd also like to introduce our colleague Tommy Cleveland, who is joining us for the Q&A session. Tommy is an engineer on Advanced Energy's solar team who performs quality assurance inspections of commercial and grid-scale solar facilities. Prior to joining Advanced Energy, Tommy worked for over a decade at the North Carolina Clean Energy Technology Center at NC State University, where he provided solar testing, consulting, and training across the state. Welcome, Tommy. We're really glad to have you here.
Thank you, Cyrus. The first question we have is about the state tax credit. Somebody's asked, didn't North Carolina have a state tax credit for solar? That's correct. North Carolina did have a significant state tax credit of 35% for quite a few years, but it expired at the end of 2015 and is no longer available. However, the way that credit was structured, corporation taking the credit had to take the credit in even installments over 5 years. So because it only ended in 2015, North Carolina is still giving out some of those credits for projects already installed. But new projects installed in 2015 or 2016 or later are no longer receiving state tax credits. This was a key policy in helping North Carolina build the solar industry that it has today. The credit's expiration hasn't had a very large impact on development of larger solar systems, but it has certainly slowed demand for the smaller residential systems that had more of a reliance on that state tax credit. For further information about the current incentives that are available in North Carolina or elsewhere, you can visit the database of state incentives for renewable energy. That's known as the Desire database, which is available at www.dsireusa.org. And that's a website funded by Department of Energy and run by the Clean Energy Technology Center at NC State.
Thanks, Tommy. We have another question regarding installation. How do I know if my home or business is a good site for rooftop solar? I'll take a shot at this one and let Tommy jump in on anything I miss. There are several factors to consider when you're evaluating it for your own purposes. One, of course, is solar access. Does your roof have good solar exposure with minimal shading over the course of the day? Another factor would be your roof condition, and this is something sometimes people overlook. If you need to replace the roof in the next 5 to 7 years, then it might be a really good idea to replace it prior to installing a solar array. And following up, thinking a little bit more about the roof, a roof installation, mounting requirements come into play. Does the solar system that you're considering require any holes to be put in the roof for attachment? If so, does that create too much risk of water leaks? Another option is that the system might be ballasted or weighed down rather than mechanically attached to the roof. And in that circumstance, you would have to assess whether the building structure can support that weight. And I've actually run into some cases where ballasted solar systems can actually weigh less than a conventional tar and stone roof. So re-roofing with a non-ballasted system or a ballasted system could give you the structural flexibility to do that with no or very few roof penetrations.
Yeah, I will add that in addition to these technical considerations, there's also the consideration of the policies offered by the utility to which you're connected. In particular, one of the most important being, or most relevant being, whether or not the utility offers net metering, which is a policy that can improve the economics of installing a solar system. The majority of solar installed in North Carolina are larger systems, which are not net metered. So we don't have a lot of net metered systems in the state, at least relative to the amount of solar installed.
That's actually a great segue, Tommy. We have a question about net metering. Does net metering make it harder to integrate solar? And at this time, it really doesn't seem to create any significant problem. I was interested to learn recently that there's actually a pretty small fraction of North Carolina solar that's net metered, only about 30 megawatts out of the 3 gigawatts, according to the Energy Information Administration. So that's about just 1% of our solar capacity in the state being net metered. And those net metered installations seem to have less of an impact on that ramp rate issue than grid scale solar does. Net metering, one of the issues around it or concerns is that it does have the potential to reduce the amount of money paid by net metered customers for the fixed or infrastructure costs of the grid. But new rate structures could easily address that, again, considering that we have a relatively small amount of it in the state.
And another question we have heard is about local solar ordinances at cities or counties and some of the trends that are occurring across the state there. There has been a trend toward those local solar ordinances, the zoning ordinance where a city or county has some regulations over the land use in their jurisdiction. There has been a trend there to require more and more robust vegetative buffers around large-scale or utility-scale solar projects. These vegetative buffers minimize the visual impact on neighbors and the community. 3 or 4 years ago, the majority of systems going in the state had very minimal, if any, vegetative buffers, and they also tended to have smaller setbacks from neighbors or other land uses. I'd say that the trend across the state has been increasing those setbacks and increasing the vegetative buffer requirements. I was involved in 2013 with a large stakeholder group that wrote a template solar ordinance for North Carolina that has no, it's not mandated anywhere. It's just truly a template or model ordinance that cities and counties can take advantage of, and many have used that as a basis for writing a solar ordinance or updating their solar ordinance. And that document is still available from both the North Carolina Clean Energy Technology Center and North Carolina Sustainable Energy Association, both of which organizations were involved in putting together that template ordinance. Most jurisdictions around the state are requiring a conditional use permit or a special use permit for the utility scale projects, but that's not true in every case. As we heard, the one example in the material today, some jurisdictions allow the projects by rights, or in some unzoned areas, there's no zoning permit required. And then one final point here is one common concern by local jurisdictions is the decommissioning of the projects and what will happen at the end of their life. A lot of jurisdictions are requiring a decommissioning plan to be required at the time of receiving a permit, and some jurisdictions are requiring a decommissioning bond where there's some kind of financial surety set aside for covering the cost or any risk that there may be some net cost of removing a project at the end of its useful life. And it's also worth noting that the county has recently enacted a moratorium, or they may have called it a ban on utility scale solar. So there's not universal agreement across the cities and counties on what's best for their jurisdictions as far as utility-scale solar. But the state has seen utility-scale solar generally covering the majority of the state.
Great. Thanks so much for that, Tommy. That actually finishes up the questions that we have. If you think of anything else that you want us to know, please do reach out to us after the webinar. But for now, I'll turn it back over to Alex.
All right. Cyrus and Tommy, thank you guys both for your expertise in helping answer some of those thoughtful questions. And thank you to everyone who submitted a question or a comment. We'd like to encourage that you share this webinar and all of the resources with your colleagues and industry contacts.